Hi, everyone. So today's lesson would be just a small introduction to data analysis in physics. So as Emilio said, if you guys have any questions throughout the presentation, please unmute yourself and you could ask a question in the chat or direct it to me. So let's go ahead. So basically, with data analysis, what we kind of try to do is find relationship between two different kinds of data. Suppose, for example, X is an independent variable and Y is something that depends. We know that depends on X. It can depend on X in a number of ways. So as you see in this slide here, it could either be a linear relationship where the slope is positive or a linear relationship where the slope is negative, or it could also be some relationship where some quadratic or exponential dependence. Or the other option is, so these relationships between data could either be really strong, as you see on the left here, where all the data is very close to this predicted line here, whereas there could be a weak dependence of Y on X in this on the right side of this plot, where you see that Y is kind of really spread out. So it kind of depends on X, but not very strongly. Another option is there could be no relationship between Y and X, even though we predict there to be a relationship between X and Y. So the aim of data analysis in physics is basically to find out these dependence of Y on X and what form it depends on. So basically how physics kind of works is based on some fundamental principles. We model certain aspects that of in nature that we know, and then we apply this model to some data that is collected by experiments, and then we try to see if the model correctly predicts the data. So if the model does predict the data, that means our model really works, and that's how nature, so nature follows this model. But then if our model does not predict data, that means we have to kick out our model and then go back to our tests and try to find a better model that fits data. So this is kind of like a small example, not from physics, but then from our daily lives, about like how regression kind of works. So this is basically a plot of the relationship between the high school graduate rate in 50 United States, 50 states in the United States of America. So from here, if we try to eyeball this data, so it kind of seems like all these three lines kind of work. It kind of predicts the data. If we by hand or by eye, if you look at this data, it feels like all these three lines predict the data. But then we need some robust system of analysis where we have to choose the best possible relationship between the percentage of poverty and the high school graduate students. So the basic idea here is you predict a linear relationship between these two, between the X and the Y axis, and then we calculate the deviation of each of these points from this predicted line. So here it will be like this point in blue, Y, minus the point in red, which is on the line. And so by adding the square of these distances from the model, we can actually predict how good our fit is. This basically gives us a deviation. And then we square these deviations because we don't, because these points could either lie further upwards away from Y, or it could either lie below Y. So we square these deviations so that the sign of the deviation does not affect our final analysis. So this basic idea is least square fit. So where we find the difference between the Y, the predicted Y, and the Y in our scatter plot. And then we square these distances to, which is the least square method given in this equation here. And then we predict how good our fit is. We try to minimize this function given by the least square method. And then depending on that function, we can predict the slope and the intercept. So for a simple model such as a linear model, it's very easy to do this by hand. We can minimize this function by hand and get a slope, an analytical form of the slope and the intercept. So, and then how do we know how good our data is? Again, if we plot the residuals is basically the difference between the intercept, which I showed you in the previous plot. And then if we plot those residuals, you can see here, if these residuals really, this linear function here, if it does not really depict the scatter plot properly, then we'll have our residuals all over the place. But then, whereas if the function on the right side, which actually depicts the data pretty well, the residuals lie pretty close to zero. So what we are about to do is basically look at some actual data that comes from the Large Hadron Collider, which is a really, as the name suggests, it's a huge collider in Europe. What they do is they basically smash particles at really high energies, and then from the outcome of those scattering experiments, they detect new particles through data analysis that we just saw in the previous slides. So basically, the question is, how is a new particle detected? So when a particle decays, this quantity is called the invariant mass. For people who are not interested in physics, basically you don't need to know this, but then just this form here, just as a small introduction. This quantity here is called the invariant mass. When a particle A decays into two particles, 1 and 2, this is the invariant mass of that channel. And then basically when the particle decays, we expect the invariant mass to be some quantity, which is given in the green line here. But then on the y-axis here is the number of detections, and on the x-axis here is the mass. So basically, if the number of detections with the mass is exactly as what we predict in the model, then that means that there is no new particle. But then if there's like some bump in this structure, it means that there are certain regions where there are a large number of particles which are coming from physics that we don't know, or physics. So that is probably like production of a new particle. So with this, I'll stop with my slides and we can go to the Kaggle notebook. If you guys saw the GitHub link, you could fork the notebook from the link.
Yeah, if you just, I think we should just give folks a second here, but if you click onto that link, scroll all the way to the bottom, click the student version, or maybe it's called the attendee version, and then you'll see in the right-hand corner of your screen when you get to the Kaggle page, an ability to copy and edit, and that will mean that you'll have your own editable copy as we go through the presentation here. So just give it a moment, and then I think we can go ahead and jump into it.
So if everyone could probably give a thumbs up in the chat if they're done with this, I can continue with the lesson.
All right, I think we're ready to go here.
Okay then, so basically, so here we have the Kaggle notebook as we've been using in the previous lessons. So for this particular lesson, you need some libraries. So the first one would be NumPy, which is used for linear algebra. And the next one is for data processing, which is called Pandas. And then for plotting, we use Matplotlib. And another important function is for regression analysis that we just saw in the previous slide. We use Curvature, which is found in SciPy. So this is really useful because we don't need to write our own functions for those minimizations. This function would directly do that for you. And then this part is just a directory. I don't think we really need this last part. So yeah, before we start, so the data that we are going to use is actually from the CERN Open Data Portal, where they actually publish their real data, the data that they get out of their detectors in a very user-friendly, readable form. So here, first, we kind of read the data, which is a CSV file here, and then after that, yeah, once all of us are there, I guess. So if you look at the CSV file in the, we see that the column M of the data set is actually the invariant mass. So the invariant mass is what I explained in the slide before, which is basically what we use for most of our detection of particles. So we go ahead and we write the variable name. So the invariant mass is, so since data set is the variable that we used for reading the files, we know that column M of the file is the invariant mass. So we do that. We set it to dataset M, and then we empty this selected list for the next part of our code. So if we fill that in, and if we just run this, we could use this run here. We could also print the invariant mass just to see how it'll be a really yeah, so here we see the invariant mass for each of these detections, so 0 to 10850. So each of these corresponds to the number of detections and then the invariant mass. So after this, we go to the next section. So basically over here, so since we know that the form of our data is like basically the number of detections and then the invariant mass versus the invariant mass, we'll try to visualize this before doing any sorts of fitting or anything. It's very useful to actually look at how your data behaves to see, to give us an intuition about what kind of forms of fit functions the data would follow. So here we kind of, so this part would be just to, so depending on the number of events that we ask, we get different forms of functions, which we'll like see further on. So this amount is equal to input is asking you an input of the number of events that you want, and then it will show you how the curve looks like for that particular number of events. So here, since we know that the total data set does not have more than a 10851 number of events, so if it asks for more than that, we have to print out an error statement. So I'm thinking about printing something like print, but then you can print anything like not more than 10851 events. So it'll give you that error. I could not plot. But then if the user asks less than 10851 events, we want to plot the histogram. So for this, what we do is we iterate over each of these events that the user asks. So for range amount, because that is what the user is asking for. And is equal to invariant mass of F, and then append selected So here we're appending M to selected because we created an empty list called selected above, and then we append to that with this M, which is the invariant mass. And then, yeah, in order to visualize, we use matplotlib. So we use this inline command so that it can directly visualize in the notebook. And then we plot the histogram. So each time we plot a histogram, we select the number of bins. Over here, I've selected 120 bins in the range 60 to 120 of invariant mass because that is the range in which we have data collected. And then for matplotlib, we set the axis here. We set the y limits, and then we set the axis with these two commands here. And then
just really quickly, on the histogram command, the number of bins, we're basically asking from 60 to 120, create 120 equally spaced kind of areas, and then we'll just count up how many things fall in that. So I guess that would be like 0.5, kind of these bins of 0.5 width, and then we just see how many observations fall in that width. So that's kind of what's happening with that histogram.
Right. So is there any questions so far? Okay, so since there are no questions, I'll go ahead. So here we set the y limits, and then we get the axis, and then after that we plot the labels. So we can plot like depending on what our histogram is. Here I've written histogram of invariant masses 2 muons, which is what we are plotting right now. And then if we quickly run this. So here, as we saw earlier, the program asks you how many events you want. So initially, if I select 50 events, let's see what happens. So as we see here, it's barely visible because 50 is really small number of events. So we don't really see anything happening. So that means that I have to increase my number of events. So if I increase it to around 1,000, let's see what happens. Okay, so now we see that there is like something going on here, but then still it's not too much to say anything. So since we know that the largest number of event is 1081, so let's try that. And now we see that there is some sort of a structure here. So with this histogram, it basically gives us a basic intuition about what kind of fit forms to use when we decide to fit a function. So
Archana, can you describe a little bit more what each of the events is? Is that what are each of the events kind of describing?
Yeah, so basically it's a particle decay. So each of these events correspond to the invariant mass of the particle. So we measure the mass of the invariant mass of the particle decay, and each event measures a different kind of an invariant mass. But then what we see here is that most of the measured invariant mass lies around 90. That's why there are like around 700 or plus more events corresponding to that invariant mass. Whereas if you look at 70, there are less than 100 events corresponding to that invariant mass. So the y-axis is basically the number of events, and the x-axis tells you the invariant mass. So from the slides that I showed you earlier, it's kind of evident that, so it seems like something is happening at 90, around 90. There's like a huge number of events that generate this invariant mass, which is probably not just, it's probably a new particle or something. Are there any questions? So I'll go to the next section. So basically here, you kind of visualize how the number of events, how the invariant mass histogram changes with the number of events. So this plot will kind of be more intuitive and clear to us now. So since we know that the total number of events is between 0 and 10851, so A should be in the range of 0. And then the increments can be in 1,000. So this gives you like the lower limit, upper limit, and the increment here. And then T is equal to. So we know that this was a variable name, and then from 0 to 8. So we fill in this. So T gets in the invariant mass from the amount that we've given. So in the first iteration, it will be 1,000, and then it will be 2,000, and so on and so forth. And then for each of these ranges, we plot the histogram again that we plot. So again, each of these, so we've been these in 120 from the range 16 to 120, as I explained. What these histograms do. And then we again set the axis and the labels. So let's see how the histogram changes with each of these iterations. So the first iteration is basically 0, so we don't expect there to be any events. And in the next iteration, we see that with 1,000 events, so there's some sort of like some significant changes at 90, but then in 2000 it increases the height at 90, and then we see that it just goes higher and higher. So so this is kind of important because many times just because of statistical fluctuations, so basically you could say that with 1,000 events, you could probably detect a new particle, but then no, because this could be a statistical fluctuation. So we want to be really sure that we are actually seeing some sort of a significant deviation there. So because of that, what we do is we try to increase the number of events and improve our statistics to be completely sure, yeah, that there is something going on in this particular invariant mass. So that's how we go forward. And then we see that finally with the largest number of events, it just peaks up here.
Is it particularly kind of like expensive to produce more of these events, or is it relatively kind of inexpensive to produce a large amount of events? Because I know like machine learning, we'd love to have more data, but getting data can be really, really expensive.
Right. Yeah, so especially in particle physics, most of these experiments are really expensive, and increasing data is basically yeah, increasing precision. Like recently, there have been like many precision calculations, and increasing precision is really, really expensive and hard because you have to take care of a lot of systematics. Yeah, so there are like billions of dollars invested in each of these detectors just to improve their statistics.
Yeah, so that's even more expensive than machine learning. Yeah, it might take like a couple $1,000s to crowdsource a couple hundred images, but definitely not in the order of billions of dollars.
Yeah, the issue is with a lot of these particle physics data, we don't have enough data to implement machine learning, even though it's been going on right now. But then, like for example, images, we can get images from anywhere. But then with particle physics data, it's very hard to get a training set which is big enough for the algorithm to learn. Okay then. So from this, yeah. So after this, like once we know that there is actually something going on here, what we try to do is we try to use regression methods, as we saw in the slides earlier. So basically, we use the curve fit algorithm, the curve fit function, which is found in SciPy. So curve fit actually requires a function that you can fit to, right? So what we do is we we look at these histograms, and then we see like what kind of function works. So from this, it kind of seems like a simple Gaussian would kind of work, because it seems around 90 there should be like a peak, and then it's pretty much flat at the other regions. So we try to write a function that describes a Gaussian. So a Gaussian, has a mean, and then it has a variance associated with it, and it has an amplitude, and x is basically the x data. So we try to return a, which is the amplitude times the exponential of, sorry, exponential.
Are we going to use NumPy for the exponential?
Yeah. So we do exponential of x minus x0, which is the mean. It's squared. Sorry. Okay. So this is the form of a simple Gaussian, which is x minus the mean divided by the square of the variance times an amplitude, which should probably give us a peak. And then we take so we input the invariant mass from 0 to the largest number of events to this variable t. And then we try to plot the histogram again, just to see how the data looks. And then after that, we define a variable called x modified, which is basically, so as Emilio explained, in each of these we have a range from 60 to 120, and we bin them, and then so that means that each of these bins has like is 0.5, has a width of 0.5. So since we want the central point of those bins as our x values, so we just add 0.25 to those, each of those values, and then we get our bin size here. And then since in this data, so in real data, we actually have errors. So these experiments are done many times, and then we have an error associated with the data. But then for this kind of training set that we had, there's no error associated. So we just calculate the statistical error, which is 1 over square root of pi, which is basically just the statistical error. It's not the real experimental error, just for our experience, we add this error. And then another thing is the curve fit algorithm requires some initial values. So we from this plot here, we think that almost, so basically A is the amplitude, and the amplitude peaks around 700. So that's why the initial value of the amplitude would be around 700. And then since the Gaussian has a central value of around 90, we give the mean value around 90. And then from this, the width seems to be close to around 2. So because of that, we give the initial value of the width around 2. And then we use the curve fit algorithm, the curve fit function from SciPy to fit the, so curve fit requires a number of parameters. The first parameter would be the function, which we defined here, which is called Gauss. And then it requires the x values, which is x modified, that we've defined, and then the y values, and then the y error, which is basically that we defined here. Sigma is basically the y error, and then so we use the y error that we actually provided it with, and then T0 basically asks for the initial values, which is And then after that, just to see how good our fit is, in the slides, we saw the value of residues. So we calculate the value of residues and plot it in the same plot just to see how good our fit is. So R is basically absolute value of Y, which is the point from our experiment, minus the predicted, which is the function, and P opt, since it's a variable which stores the optimized parameters, we minus, so basically it's the Y value minus the predicted Y value, and the absolute value of that would give you the residues. And then this
really quickly, just to be clear, because we're dealing with a bunch of NumPy arrays, all these operations will be vectorized. So like Y is a vector, what the Gauss is going to be applied element wise, and so that's going to be a vector of predicted values. And so I guess R is it correct to say R is also going to be kind of the residuals vector?
Right. Yes. So that is the good thing about using NumPy and Python, where you don't really have to apply for loops and go over each element. It would directly do the vectorized calculations for you. So R is basically the vector of invariant mass for each of these X points. Okay. And then after that, we plot we plot our model, and then we also plot the residues on top of the histogram to see. And then we print the mass, which is, so since the second term here is x0, so x0 is probably the mass, and then sigma is the last term, which is probably the width of this Gaussian, which is, so if we run this, let's see what it's,
I think maybe the Gaussian had the wrong sign in the argument.
yeah. It's this. Yeah. Yeah, thanks. Yeah, so here, sorry about that. So basically, yeah, Gaussian is minus the value. So from this, we see that, so we see the plot. So this orange curve here is our fit, and the blue lines here is a histogram, and the green point here is our residue. So what we see is that our curve kind of explains the region around the peak pretty well, but then the region outside the peak is not really explained that well. That's why the residue is pretty high outside the peak, but then within the peak it goes down. And then again, it kind of increases outside the peak. But then so the outside the peak is basically background background effects, which we are not considering in this plot. So we don't need to really worry about that. So if we set our X limits, in order to zoom in and see slightly better, we could probably set X limits from around 85 to probably around 100 and see how it behaves. So yeah, here we go. So we see that around the peak, this Gaussian pretty much explains our data pretty well. And the mass that we get out of here is 90.86, and the width that we get is 2.88. So so generally what we do in particle physics or in any kind of physics is we try different models just to test our data. So we could probably add a different model here and then to see how that predicts our data. So similar to what we have here, if we try to add another function. So here we have, I kind of copy paste this part of the function to this thing. And instead of Gaussian, if we have like a Laurentian, So which is basically, which also has a width and a sigma associated with it, which is an amplitude times, so a Lagrangian function would be 0.5 times width and times initial divided by x, x, y, z. So if we define another function called Lorentzian here, so which also kind of has a peak in its structure. So we could define probably this way, just to be consistent. And then we basically do the same thing here. We do t is equal to invariant mass from 0 to 10851. And then we plot the histogram just to see how our data looks. And then we can plot the function on top of the histogram to see how well our data, our model describes the data. And then again, we have x modified, we define our y error, and then initial values. So the initial values would not change much because there's also the amplitude and the mean and the width would also probably be. But then over here we have sigma squared, so probably the width is 0.4. So, and then we do the same thing. We have our optimized parameters from the curve fit function. And but then here our function is different. So we try a lens. And then again, here our function is a Lorentzian. Here as well. And then we get the mass. So if we try to run this. So our initial parameters could be yeah, so sorry about that. So it's plus sigma here. So once we have that, so again, we see that the mass is kind of very close to the mass that we had earlier. So earlier we had mass of 90.86, and here we have a mass of 90.88. So with different models, we kind of get the same mass, which is good news. That means the mass is probably right. And then the width. Okay, so the width here in the Lorentzian is basically square root actually. So I do NP dot square root. So the width here is 2.09 and the width here is 2.88. So there is a small discrepancy in the width. So that kind of means that we don't really, we're not estimating the width that well probably, but then the mass predictions are pretty robust.
So what is the width kind of conveying to us? What about this particle that we're potentially discovering? It does the width kind of what does it connect to?
So it's basically the decay width. So it can be related to the half-life. So when a particle decays, it's basically the just like how in an RF circuit we have like a width associated. So it's basically the half-life of the particle. Yeah, so with this we get the height and we get the mass and the width. And if we want to really compare it with the actual mass, so the real mass of the Z boson is 91.18, which is very close to the mass that we predict from this analysis. So that means with this data, we can actually, we've actually discovered the mass of the Z boson to be 90.88, which is pretty close to the actual mass. So yeah. So are there any questions so far about either about regression or about the model that we've used or about the data or anything?
Did have one more question. How much will we have to do to be convinced that what we're looking at is, I guess that would involve a statistical analysis and starting to pull in like p-values, but I assume we would want to see, we'd want to be like very convinced, right? I assume like my p-value from social sciences of like 0.1 is not going to cut it.
Right. Yeah, so basically the rule of thumb is if we have like a 5 sigma deviation from this background, we kind of say that there is a detection. So the rule of thumb is basically having a 5 sigma deviation from the background. So in a real analysis, what we do is we fit this background radiation. So this, which we've kind of not in this small sort of analysis, we've kind of omitted that part. And then from the background, if there's like a 5 sigma deviation, which is clearly present here, then we see that, okay, there is something going on in that region. The rule of thumb is like having a 5 sigma deviation.
And so for the researchers that kind of initially pursued this, was it, I don't know if you know, but was it like immediately this clear that they saw a particle? Or I assume, I know a lot of the effort went towards kind of building the LHC. Was it kind of like, okay, now we have it built and like, okay, we've observed it now, like we know that that's something?
Right, a lot of initially we didn't really have a lot of statistics. So I guess the first particle accelerators at SLAC, what they did like see something, they did detect particles, but then some of their channels had very less statistics. So what we're doing right now is even at Jefferson Lab, which is very close to, which is in Newport News, what people are doing down there is trying to improve statistics in certain channels and to be completely sure that something is actually going on there and pin down the precision of these masses. So as we see, like with the number of events, your statistics actually changes. So for example, even in this small example, if over here we have t is equal to 0 to 10851, if we try to reduce the number of events to maybe like 800 or something, maybe even lower 500, we probably won't see a good fit. So here, I mean, actually for this particular thing, there is a good fit, surprisingly, but then let's see if we go down. But then you see that the width, the uncertainty in the width keeps on increasing, like the width is way off. But it seems like the mass is pretty spot on, which is really, it's actually surprising. Also, yeah. But then with increasing number of events, we can actually pin down the mass and the width to a greater precision, as we see here. Like, so if we play around with the number of events here, it's kind of evident that we need a huge number of statistics to actually. Yeah. And with this, we get to pin down the width even better. Yeah, so one of the major efforts is to improve statistics and basically get the values of each of these, the mass and the width of particles pretty spot on.
Great. Well, if there aren't any kind of more questions lingering here, I guess we're done a little early. That doesn't usually happen, but you know, stick around if you have any questions for Archana or about DSC. And thanks for coming out, everyone.